Hey, welcome back to chemistry. And so in this presentation, what I want to do first is talk briefly about the modern view about the structure of the atom. And once I've done that, we'll talk about the ways we symbolize different kinds of atoms. And so I'll be talking about something called atomic number, mass number, and isotopes. And then finally, the last thing I want to talk about is how we measure the weight or mass of an atom. Okay, so here I have a picture of an atom on the screen. So that gray spot is a picture of the atom. So atoms are very small, and so I actually have a value there for the radius of an atom. And the radius of the atom is going to be about 1 × 10⁻10 meters. And so I think that's hard to really sort of understand, at least for me. And so I want to give you sort of a brief demonstration to give you a sense of just how small atoms are. Okay, so here I have a cantaloupe. This cantaloupe is made of atoms, and the 4 elements that are largely found as atoms in the cantaloupe are carbon, nitrogen, oxygen, and hydrogen. Now the first 3 have about the same size. Hydrogen's a little bit smaller. Now let's say, for example, we say nitrogen is sort of the average size of the atoms of the cantaloupe. That's probably a fair guess. Now, to give us a sense of just how small an individual nitrogen atom is, imagine we took an individual nitrogen atom in the cantaloupe, one of those tiny little atoms in the cantaloupe, and we blew it up to the size of a blueberry. If each atom was the size of the blueberry, what would be the size of the cantaloupe? Would it be the size of a car? No. Would it be the size of a house? No, even bigger than that. It'd be the size of the entire planet Earth. So that really gives you sort of a sense of just how small atoms are. Now, another thing to sort of understand is how small the nucleus is to the size of the rest of the atom. And so again, here's my blueberry here. And so there's going to be, say, in an atom the size of a blueberry, there's going to be a small nucleus in there. So if you were to even use the most powerful microscope available, you would not be able to see the nucleus. It's very small. Now, if you were to blow up this blueberry to be the size of a house, and you might be able to see a nucleus at that point. But if you were to blow up this blueberry to be the size of the Commonwealth Stadium, and that would be this blueberry being the atom, then the nucleus would be the size of a marble. So that gives you sort of a sense of just how small atoms are, and nuclei are even smaller than that. And then, as we kind of discussed before, in the nucleus of the atom, you have 2 subatomic particles. Those are protons and neutrons. Neutrons have no charge, protons have a positive charge. And then outside of the nucleus, and all that space that's beyond the nucleus, that is where the electrons reside, and the electrons have negative charges. Okay, so now let's go ahead and take a careful look at this table. And this table gives us sort of a relative idea of the amount and charge that each of these subatomic particles have, and also the relative mass that these subatomic particles have. And so what you can sort of see there is that, look at the charge there. So the charge there, you can see that the neutrons have absolutely no charge, and so they're considered to be neutral. Protons have a positive charge, electrons have a negative charge. Now, as for the magnitude of charge, you will notice that the protons, the electrons, despite the fact that they have opposite charges, they have exactly the same magnitude of charge. It is 1.602 × 10⁻19 coulombs. So that's a very small amount of charge. So both protons and electrons have a tiny amount of charge, and it's exactly the same magnitude. It's just an opposite sign. Now, you can also sort of see the relative masses of these subatomic particles. The electrons are a lot smaller than the protons and neutrons. In fact, the electrons are about 1/2000th the mass of the proton. The neutrons are about the same size of the protons, but they're actually maybe just slightly larger. So now I want to talk about how we use symbols and designations to represent the different atoms in the periodic table. So one thing you need to be aware of is when you're looking at a periodic table, you will probably often see a number toward the top of each box that represents each element. And that number will be an integer. It'll be 1 all the way up to 108. That number there is called the atomic number. That number tells you the number of protons in that element. So for example, hydrogen has a number 1 if you look at the box where hydrogen is contained in the periodic table, and so it has an atomic number of 1, and that indicates that all hydrogen atoms have 1 proton. Helium has an atomic number of 2, and therefore it is a different element because it has a different number of protons. Lithium is a different element, and so it has a different atomic number. It has atomic number 3, it has 3 protons. And so in this example here, we have copper, which has an atomic number of 29, which indicates that it has 29 protons. Okay, the next number you need to be aware of is something called the mass number of an atom. So the mass number is symbolized by the letter A. The mass number is equal to the number of protons and neutrons in an atom. So one thing that you'll be often given, say on a test, is you'll be told that an atom has a certain atomic number and it has a certain mass number. And you might be asked to figure out the number of protons it has and the number of neutrons it has. Well, figuring out the number of protons it has is pretty easy. The number of protons is just equal to the atomic number for that element. But how do you figure out the number of neutrons? Well, to figure out the number of neutrons, you just take the mass number for that atom and then you subtract the atomic number from it, and that should give you the number of neutrons. So here I have sort of an example of 3 different kinds of carbon atoms that you can find in nature. Now they're all carbon atoms, and so they are all the same element, and so they will all have the same number of protons, which is 6 protons. But they're a little bit different from each other. The way they're different is they have a different number of neutrons. So carbon 12 has 6 protons, but it also has 6 neutrons. Now, 6 protons, 6 neutrons, that tells you what the mass number of that carbon atom is. The mass number is 12, and so we call it carbon 12. Now, another kind of carbon atom you can find in nature, although there's not nearly as much of it, is carbon 13. It is carbon, so it has 6 protons, but this carbon atom, each of those atoms will also have 7 neutrons. So the mass number for each of those atoms is not 12, it's 6 plus 7, it's going to be 13. And then there's carbon 14, and so that will have 6 protons and 8 neutrons. Now one thing I want you to sort of notice there is that these 3 different carbon atoms that are found in nature, they're all carbon. Again, they all have the same atomic number, so they're all carbon, and the atomic number is 6, and so they will all have 6 protons. But they have a different number of neutrons, and what that means is that each of those atoms, carbon 12, 13, 14, will have a slightly different mass. So carbon 12 has 6 protons and 6 neutrons, so between the 3 of them, it has the lightest mass for a single atom. It's 1.99 times 10 to the negative 23 grams. Now carbon 13 has 1 more neutron than carbon 12. It's going to weigh a little bit more. It's 2.15 times 10 to the negative 23 grams. And carbon 14 has another neutron. It's going to weigh a little more than that. It's 2.32 times 10 to the negative 23 grams. So here we have an example of atoms of the same element that, because they have a different number of neutrons, have a different weight. When you have that, you have something called an isotope. Well, an isotope is our atoms are the same element, but because they have different number of neutrons, they will have different masses. So again, isotopes is the case where you have atoms of the same element will have different masses because they probably have a different number of neutrons. And so I have, again, the samples of examples of carbon isotopes there are carbon 12, 13, and 14. There's sort of pictures of that there. So in general, you should know how to write out the isotope in a nuclear symbol. And so X indicates where the abbreviation for the element would go. And so with carbon, the abbreviation or the symbol for carbon is C, so that would go on the X. The lower left number is the atomic number. The upper left number is the mass number. So you can see in that diagram over to the right, all those carbon isotopes, carbon 12, carbon 13, carbon 14, they all have the lower number being 6 because they're all carbon atoms, and therefore they are the same element, and have the same atomic number, but they have different mass numbers, 12, 13, 14. And again, it's because they have increasing number of neutrons, and so they will have slightly different masses. And so again, those are the isotopes of carbon. So I just kind of indicated what all those letters are in the symbol. So at this time, what I'm going to do is I'm going to write on the screen, and you're probably going to see something like this on your test. You're going to be given some pieces of information about an atom, and you're going to have to complete all the information based on the pieces of information you have. And this will depend on your knowledge of atomic number and mass number and how we write them out in terms of symbols. So let's try this out. Okay, so in our first example, we have some kind of atom with 4 protons and 6 neutrons. And so you have to fill out the rest of the spots. And so for all these examples, you should assume that the atom is neutral. And if it's neutral, that means there are going to be as many electrons as protons, which means there'll be as many negative charges as positive charges. So let's go ahead and fill out this table. So with this first row, since we have 4 protons, that indicates we have 4 positive charges in the nucleus of this atom. If it is a neutral atom, which this problem suggests, then it should have an equivalent number of electrons. So we should have 4 electrons as well. Now, what is the atomic number? So you remember that the atomic number, all that is, it's the same as the number of protons. So if we have an atom with 4 protons, that means its atomic number is 4. What is the mass number of this atom? It's just simply the protons and the neutrons added up. So the mass number should be 10. Okay, so now you're going to have to draw out some notation for this atom. One will be a nuclear symbol and one will be hyphen notation. So to do that, we first need to identify what element it is. And you would have a periodic table to solve this problem. But the way you know the element is you know that every element has its own atomic number. So if you look up atomic number 4 in your periodic table, what you should see that this element is beryllium. So with the nuclear symbol, I'm going to put a Be here. This is beryllium. And for the atomic number, that is the small number on the lower left. So there's a 4 here. That small number on the lower end can be called a subscript. And then we have a number on the upper end, and that number will be called a superscript, and you will remind yourself that the superscript is not the number of neutrons. What it is the mass number. So the superscript should be 10. Now, when you write out this atom in hyphen notation, what you do is you write out the name of the, oops, spelled it wrong, beryllium. There we go. That is correct, I hope. Beryllium. You write that out, and then you write out the mass number 10. Okay, so let's go on to the next one. Okay, so now we have an atom that we know has 29 neutrons, and it has an atomic number of 27. So can we complete the other spaces? Well, if the atomic number is 27, then we know that the atomic number is the number of protons. And so the number of protons should be 27. Now, do we know the number of electrons? We do, because we know this is a neutral atom, so this should be 27 electrons. So what is the mass number? It's going to be the number of protons plus the number of neutrons. So the mass number, 29 plus 27, is going to be 56. Okay, so we're now, to write out the nuclear symbol in the hyphen notation, we have to identify what this atom is. And so if we have an atom with 27 protons, I just know that that happens to be cobalt. You can look it up in your periodic table. The symbol for cobalt is CO. So the atomic number goes on the lower left corner there. The atomic number is the number of protons. Again, the lower left number is 27. The mass number is the upper left number, which is 56. And then in hyphen notation, you write out the element, which is cobalt, and then the mass number, which is 56. Okay, the next one we have the hyphen notation being potassium 41, and we also know that the number of electrons in this atom is 19. So can we get some more information? Yes. So recalling that these are neutral atoms, if we have 19 electrons, what that means is we also have 19 protons. Now, can we figure out the number of neutrons? We should be able to, because in that hyphen notation, we see what the mass number is. It's 41. So what is 41 minus 19? Let's see, that's going to be 22. Now, what is the atomic number? The atomic number is just equal to the number of protons. So the atomic number is going to be 19. The neutrons is 22, so the mass number is 19 plus 22 neutrons, so it's going to be 41, which we already knew from hyphen notation, I guess. And then what is the nuclear symbol? It's just the symbol for element, which is potassium K. The atomic number is 19, and the mass number is 41. Okay, so our last one there, we have a nuclear symbol that indicates that this element we're dealing with is sulfur. It has a mass number apparently of 34, and because that's the upper left number there, and we're also told the number of neutrons, which is 18. So we know we have sulfur, 34, so I'm going to write that out, sulfur. So let's try to get some more information. So you can look up the atomic number, the number of protons of sulfur in the periodic table, or actually you can calculate it. The way you calculate it is just simply taking the mass number, which is the protons plus the neutrons, which is 34, and subtracting the number of neutrons, which is 18. So that should give us the number of protons. So the number of protons should be 16. So if this is a neutral atom, it should have 16 electrons as well. The atomic number is 16. And the mass number, again, is protons plus neutrons, which we already knew is 34. Okay, so now we will move on.